I'm doing a certain velocity. And what's that velocity? Our next step is always to take the d. It tells us what goes there. Well, the 5 meters goes there. And what goes in the t? Oh, the 5 seconds go there. Well, I've got a 5 over 5. How many 5s are there in a 5? Oh, there's only one. And what's left is meters per second. And remember I also told you that the division sign, we can always often say per, instead of meters, 1 meter divided by seconds, 1 meter per second. And we know that that is a velocity. And in case you forget what meters per second is, you go back to your chart and you see, oh, meters per second. That's telling us it's a velocity. All right, so let's get back to our discussion on motion. Now that we know the tools that we're going to be using and the rules, I said that motion is intuitive. It's automatic. We can see things moving. When things move, we can see them more readily. If they're staying still, sometimes, especially with the right camouflage, we can't see them. And that's why that little baby fawn, the little deer, uh, can hide in the bushes very, very well. And here's my little deer hiding in the bushes. Okay, he's lying down as his mom runs away. Okay, because if he stays very still, he's got these dots on him. If he stays very still, he can't be seen in the brush. But if he moves, and one of those dots changes position, then he can be seen. Okay, so motion is measured with respect to the background. But how about acceleration? We said we can't feel velocity. We said that velocity is in constant motion. Constant, that's my abbreviation, motion, we can't feel. Can't feel it. And we said the fact is that we are moving around. The Earth is spinning at 1,000 miles per hour, and we can't feel it. But I also said there's another kind of motion. This is constant motion, but there's also a changing motion. Let's call it a changing velocity. And a changing velocity, which is equal to a v final minus v initial, if that happens over a certain time, we call this an acceleration. And this we can feel. Our bodies can feel this. Okay? Well, just gave us another formula. A is equal to a change in velocity over time. And that is the same as A is equal to V final minus V initial. Again, it means start initial over time. And we can feel this. We did a demonstration in class, so you could really sense an acceleration. I had someone sit in that chair in the front of class, right? They happened to be holding water. Could have been worse. You could have been sitting in a car holding some hot coffee. And I gave the exam, and that person, I moved along very, very carefully, very slowly. They happened to be sitting in a chair, and the chair had rollers on it. And they were sitting in that chair like this, their feet up, holding water. And while I moved at a nice constant velocity, and I'm going to show a constant velocity using that other thing we learned about, vectors, And here was the first velocity, and then the second one, and the third one, and the fourth one. They're all the same magnitude, which means they all have the same value of v. This v is equal to this v, and v is velocity. That's our symbol for velocity. And as the wheelchair moved along, the water did not spill. It was fine. But then I started off from 0. Okay, and here's my velocity again. I started off with this velocity. Not even quite that. Let me undo that. I started off with this velocity. And then, in a little while, my velocity was this. Then it was this a second later. Then it was this. If these are vectors, the direction may be the same. But are the values the same? Don't forget, the magnitude is the length, the size is the length. And what this says is that it's getting bigger and bigger and bigger. So I can't put V over here anymore. I've got to put this as maybe V1, V2, because they're all different now. V3 and V4. They can't have the same name because they're different values. And this represents a changing velocity over time. This is a change in V over T. Hey, wait a minute. We know what that is. That's an acceleration. We got it right here. So this showed an acceleration. And when I did that, what happened to the water that was up to the brim over here? Was he able to feel a big change? Sure, he felt it. What happened to the water? Well, you remember what happened to the water. But all of us, even though there was only one volunteer who sat in that chair and moved, we've all sensed this before. We've sensed that if we start off really, really slow, we cannot feel velocities. Remember Grand Central Station and the train? All of a sudden you think the wrong train is moving, and you realize it's you that's moving. Or if you come into a tunnel on a very quiet, smooth train, you don't realize how fast you're going until those lights speed by. But an acceleration you can feel. And we demonstrated that in class. So now we have, and don't forget these are all symbols because this is a formula. Okay, and these are all measured in meters per second, which are the units. Okay, and these were our vectors showing us what we were doing. Okay, now acceleration has, we said in class, it has different kinds of units. Let's look what the units for acceleration are. First of all, I'm going to put the units in this formula. A is equal to V final minus V initial divided by time. Just the units now. Meters per second divided by seconds. Those are our units, right? Velocity, meters per second. We'll subtract them, end up with a certain meters per second value, and time equal to seconds. Remember I told you our secret? We're not going to tell anybody else. So we'll have, when someone says divide these two fractions, we're going to know exactly how to do it and do it real quick. And remember we said that let's divide 1/4 by 1/2. And I said the rule was, that you remembered from maybe grammar school, is 1/4 divided by 1/2. That's what we have. Okay, and what I was going to do is keep the first one. We're going to keep this 1/4 we are going to change the sign to its opposite times, and we're going to flip the last one. And then we're going to solve it. Now, multiplying out, we have 2 over 4, which is the same as 1/2, and that was our final answer right here. Okay? And we also could have said there's 2 up here, 2 goes into 4 2 times and multiplied it out, it would come out the same. Let's do one more to make sure we got this. And remember our rules. Keep, change, I'm going to put the change symbol in here, and flip. All right, we did this in class quite a bit, so I'm not going to belabor it. I'm going to do one more example, except this time I'm going to use letters. Meters per second divided by seconds. Meters per second divided by seconds. Okay, keep the first one. Change the sign and flip the second. And multiply it out. Meters per second squared. Hey, wait a minute. We've seen this before. Where do we see this before? We saw it somewhere. Where do we see this thing? Oh yeah, over here. Meters per second squared. Right there. Meters per second squared is an acceleration. Here are the units. There's what it is. And there is what meters per second squared is. So let's go back to our last page now. Now that we know what that was, we can now understand a little bit more how these units work and how we end up with meters per second being meters per second squared. Okay, we talked about quite a bit in this about this in class, using our rule for division of fractions. And we said that we've often heard acceleration called, even in 8th grade, meters per second, and that's the same as meters per second squared, and that these are nothing more than a name of the number that goes in front of it. Okay, meters per second squared, if I have 10 meters per second squared, this is a name saying, oh, I have an acceleration of 10 meters per second squared. It does not mean you take the squared and square the 10. This is not a mathematical operation. This is a name. And we did lots of these. So we know that the names are the units. And as we go through high school, we'll find out using these units often tells us if we have the right formula.